Welcome back. In this second video, I'm going to be talking about the transition from sensation to perception, which is finalizing some topics on sensation, then laying foundations to the next topic, perception. So we all experience lightning. Now, pause here for a second and think about how long do you think one lightning lost? How long? Well, typically people say 1 second. Again, 1 second equals 1,000 milliseconds. The actual event itself is not more than 200 milliseconds, 1/5 of a second. Roughly, one lightning has three or more bolts. Plus, there is a 50 millisecond of interval between the bolts. So, one lightning, assuming it has four bolts with four intervals, four bolts for 4 milliseconds, and four intervals for 200 milliseconds, roughly 204 or 200 milliseconds is how long a lightning lasts. But we experience more than that, 1,000 milliseconds. The question is, actual event is for 200 milliseconds, but our experience is for 1,000 milliseconds. The question is how? Let's answer this question. We experience the lightning longer than its actual duration. Well, our experience of lightning reflects our perceptions of the event, not the actual event. Our perceptions and the actual event, there is some mismatch to some extent. The question is, how can you experience an event for longer than its duration? Well, the only explanation would be if there is a system that holds the event, which gives us a chance to experience the event for longer than its duration. And guess where this place is? You're right, it is in the sensory system. In case of lightning, it's your visual sensory system. Your eyes, the retinal photoreceptors in your eyes hold information for longer than its actual duration, resulting in our experience. Visual persistence is the persistence of visual information beyond its existence in the real world. Visual persistence is because of visual sensory memory, your retinal cells, also called the iconic memory. The outcomes for this unit is talk about how much of information does your visual sensory memory hold, for how long, and how is the information lost. Then we'll talk about what exactly happens during a fixation and from one fixation to another fixation. How much of information is held in visual sensory memory. Keep in mind, when we say how much, we are not measuring the amount of information by itself. We are actually measuring the amount of information in relation to the information that is available in the external world. Our eyes have a one-on-one correspondence with the visual field. In other words, if you look straight, whatever you kind of see, starting from your left to the right side in a semicircle fashion, that's your visual field. And your retina has a one-on-one correspondence with the visual field in the sense that for every point there is in the visual field, there is a corresponding point in your retina. In other words, 100% of information in the visual field is captured by your retinal cells. The question is how much of this 100% of information is held in your sensory memory for a brief period of time? That's the question. Everything is held, we know that, but of that, how much of it is held for a brief period of time sufficient for us to be able to attend to and do the perception part. Initially, researchers thought it was very little, which is percent. Now we know that it's a lot more than that. It's actually 76% of the information. In other words, now we know that 76% of the information out there in the environment is held at least for a brief period of time, which is like 100 to 250 milliseconds. And we know about this based on some beautiful experiments by Sperling. Sperling's iconic memory experiments are well known, and we can talk about two such experiments which give us information about these two different answers to this question, how much. Okay, let's do a small task here. In the next slide, you'll see an array of letters. When I say array, it's a matrix of letters. And your task is to remember as many letters as possible from this matrix. Please do not write it down or rehearse. In fact, you won't get that time. It will be briefly shown to you. Remember, we are trying to measure how much of information is held in your sensory memory. The moment you rehearse information, then it becomes a part of your short-term memory. So there will be a very brief presentation of information. Are you ready? Okay, here we go. Okay, now take a moment, write down as many letters you remember. I'm gonna give you a few seconds here. Write it down. Yes, write it down. Let's see how many you got. Well, here is the answer. You see, how many do you remember? Typically, people say 4 to 5 items out of 12, which is 37%. This is called span of apprehension, the span of attention, or the span of immediate memory. 4.5 letters is what people typically remember from a matrix of 12 items. This is true when the participants were asked to recall immediately, like you did, or after a delay of 500 milliseconds. Or even after a delay of 5 seconds, people report 4.5 letters. According to this experiment, then, it seems like we only remember 37% of information. Now, let's go to the next slide where we'll talk about experiment 1 in Sperling's 1960 published study. There are two experiments. The first experiment is about the whole report condition. What we just did is Sperling's iconic memory whole report experiment. Then we'll talk about the second experiment, which is the partial report condition. Then we'll make inferences about what we know about how much information is held in sensory memory. Remember, this is all about answering this question, how much. So in Sperling's iconic memory experiment whole report kind, the task of the participants is to recall as many letters as possible. So first, just like you did, participants will be presented with letters in an array. Then they'll be presented with a blank screen, followed by typically participants remember 4 to 5 items. What Sperling found was that the x-axis here is the number of items presented. Either there were 3, 4, 5, 6, or 7, or 8, or 9, or 12 items presented. So they manipulated the number of items presented, and the DV was recall accuracy. You can see the recall accuracy is also in terms of numbers. As you can see, when there were fewer items, the accuracy was fine. With the increase in number of items, there is no corresponding increase in recall. In fact, it drops. In other words, with the increase in number of items, the accuracy drops, and the average is around 4.5, suggesting that we lose most of the information. In fact, only when there are fewer items we are able to remember 100% of the information. As the number of items increase, our accuracy drops. What it means is that our eyes capture so much of information. In fact, when you look at the 5, it's actually 37% of the information overall. In other words, according to Sperling's iconic memory experiment of the whole report kind, the conclusion was that our eyes capture 37% of the information that's out there in the environment for a brief period of time. That's very less. Now, what Sperling did in his second experiment is like, wait a second, if the whole report experiment concluded that 37% of information is what is reported, is it same as what is held? He wanted to check if visual sensory memory is holding 37% of the information, or is it holding more than 37%, but by the time people recall information, most of the information is lost. What remains is the 37% that is reported. In order to examine this question, he devised another experiment, the Sperling's iconic memory experiment of the partial report kind. The first experiment is called a whole report kind because participants were asked to remember as many items from the list of items given to them. Whereas in this experiment, participants were asked to report a specific row of information. That's why it's partial report condition. Task is same as the first experiment, except that here the task is to recall only one of the rows, letters in one of the rows. What they did is first participants would see an array of letters, and it's always 12, unlike the first experiment where they were presented with varied number of items, 12 number of items, followed by a blank screen for a varied amount of time. Then the beauty here is participant now would hear a sound, and that sound would be a cue. And the tone of the sound was manipulated so that it was either high pitched, medium pitched, and low pitched. Just imagine they would see 12 items, an array of letters, then a blank screen for a varied amount of time, followed by either high pitched sound, medium pitched sound, or low pitched sound. High pitched sound would be a cue to recall the first row of letters. A medium pitched sound, the second row of letters, and the low pitch sound would be a cue to recall the third row of letters. Then participants recall that row of letters. The DV is the recall accuracy. What they manipulated was the tone of the cue. In other words, they sometimes heard high pitch sound, sometimes they had medium pitch sound, sometimes the low pitch sound. What they also manipulated was the cue delay. In other words, for how long they saw the blank screen before they heard the sound, so that this information had to be held for 0 milliseconds, for 50 milliseconds, or for a second. So they manipulated how long this information had to be held before they could actually hear the tone, which would be a cue for them to select a part of the letters they need to recall. The next slide, we'll look at the results of this study. Here are the results. The x-axis presents the delay of the. Remember, in some trials, they heard the sound immediately after the presentation of the blank screen. In other cases, it was either 0.15 second, or 0.3 second, 0.5 second, or 0.1 second, so on and so forth. So the delay between the presentation of the cue and the presentation of items was manipulated. The y-axis is the number of letters, raw number of letters. How many letters did they recall out of 12? Remember, there were 12 items. What they found was the participants were asked to recall immediately after presentation of the blank screen. In other words, there is no delay between the presentation of the items and the cue they heard. The accuracy was 3 out of 4 items. And why do we say 9 here? Well, keep in mind this is any row. Participants were presented with the 12 items, but they were only asked to recall from a given row. If you generalize that to 9, it would be 9 items, because participants didn't know from which row they would be asked to recall the items. They had to retain all 12 items, and then they were asked to recall the items from a specific row. So if their memory for a given row is 3 out of 4, that means that it is 3 out of 4 for any of the rows. What they found was when the delay was only 0 milliseconds, that is immediately after presentation of the items, participants remembered 3 out of 4, 9 out of 12, that is 76% of the information. But as the delay increased between the presentation of the items and the cue, as you can see, the accuracy dropped. And by 1 second, the accuracy dropped to 4.5 items out of 12, which is 36 to 37%, which is equal to the whole report condition. You see that? Which means that the reason why participants were only able to report 37 items in the first experiment of whole report kind is because most of the information was lost in a second before they could actually recall. In other words, we now know that the visual sensory memory actually holds 3/4 or 76% of the information out there in the environment. And most of this information is lost before one can start reporting these back. So how much? 76%. Now, coming to the next outcome, we know how much of information your eyes hold for a brief period of time. The question is, for how long, for how brief of a time is this information held? Where your eyes will fixate for 200 milliseconds, then they move and then fixate again. In other words, during the fixation of 200 milliseconds, your eyes will capture information only during the initial 50 milliseconds. And for the remaining 150 milliseconds, and also during a saccade, which is 50 milliseconds, so roughly 200 milliseconds or 250 milliseconds, the information is held before new information comes in. So for how long the information is held in your sensory memory then? Well, according to this, information captured by your eyes is held for 200. And this is captured here, right? So if you don't include this part, it is 200 milliseconds. If you include this part, 250 milliseconds. So you say the information is held for 200 to 250 milliseconds. That leads us to the next question. How is this information? What happens to this information after 200 to 250 milliseconds? Is it erased by new information? Or is it just lost by sitting there? So that leads us to the next question. How is the information from your visual sensory memory lost? And there are two possible ways of losing information: decay or interference. And we keep talking about this over and over again about decay or interference. Information can be lost from any memory system, including sensory memory, in two possible ways. Decay is when the information gets lost over the passage of time by disintegration, right? Or through interference. Decay, for example, look at an object in the room, any picture or anything, and try to hold that information in your head. Now close your eyes. Try to hold it. After some time, it disappears. This way of losing information is called decay, where the information is simply lost because of the passage of time. The memory traces disintegrate over time. That is decay. The other possible explanation for why you might lose information from any memory system is interference. Interference is when other information is knocking this information out. So how do you think, by just looking at this picture, the information gets lost from your visual sensory memory. You're right, it is through interference. Interference, new information from the second fixation erases the old information that's captured in the first fixation. This is called backward interference, when new information goes backwards and erases the old information. It's called backward interference, also called backward masking, because we don't just read a sentence, close our eyes, right? In that case, it will be lost through decay. We actually continue to read the sentence from one word to another. In other words, the new information is erasing the old information. Okay, to sum up then, what exactly happens during a fixation? Well, as you know, your eyes fixate on words. Every time it fixates on a word, it captures information. It fixates for 200 milliseconds roughly. During this 200 milliseconds of fixation, it captures information during 50 milliseconds. For the remaining 150 milliseconds, your brain attends to and perceives what is captured. Then your eyes move to the next word and another fixation with capture of information starts. Now here's the question. It's captured information, 76% of the information. And out of this, your mind attended to a part of the information. And out of this part of the information, your brain has perceived a part of that captured information for 150 milliseconds. Now, what happens to this part of the information that is attended to for 150 milliseconds when your brain actually perceives it? Because next, it goes to the next word and the process repeats. What happens to this information? Well, this information, the whole information and the part of the information, the part of the information goes to your short-term memory. Then your mind captures, your eyes capture again new word, new information. Most of it is captured and a part of it is again attended to and perceived, and this perceived information goes to your short-term memory, and this process continues. As we say, we know that from each fixation you're selecting a part of it and perceiving it. That perceived information is sent to the short-term memory, right? In other words, does it mean that we carry information from one fixation to another fixation? Yes, we do. We do carry information that you've captured, but not all of it, only a part of it, right? Which we perceive is this memory is held in your short-term memory, even when your brain, your eyes are going through saccades. This memory for information that is attended to, that you carry from saccade to saccade in your short-term memory, is called transsaccadic memory. It's called transsaccadic memory. Trans is across, saccade is saccade. You have memory of a part of the captured information in your short-term memory, even during saccades, and that's called the transsaccadic memory. And this information is held in your short-term memory as object files. Well, this begs another question then. If you only remember a part of the entire captured information, what about the rest of the information? Do you not recognize, store information about the rest of the visual field? Well, it seems like you don't remember, but how do you process it? In other words, if you change the rest of the information that's not captured while you're going from one fixation to another fixation, do you not recognize the change? And it's kind of abstract, right? Let's make it more concrete and talk about it in terms of not reading, but in terms of a general visual perception. So what I'll do is I'll give you some time so you can go to the next slide, right? And watch this video. After this, we'll talk about these constructs again. So here's the video. I want you to watch this. I want you to watch this video carefully. And once you're done with this, I'll see you in the next slide.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, arrest Lady Smythe.
How did you know?
Madam, as any horticulturist will tell you, one does not plant petunias until May is out. Take her away.
Sorry, madam.
It's just a matter of observation. The real question is, how observant were you?
Action.
Clearly, somebody in this room murdered Lord Smythe, who, at precisely 3:34 this afternoon, was brutally bludgeoned to death with a blunt instrument. I want each of you to tell me your whereabouts at precisely the time that this dastardly deed took place.
I was polishing the brass in the master bedroom.
I was buttering his lordship's scones below stairs, sir.
Why, I was planting my petunias in the potting shed.
Constable, Arrest Lady Smythe.
Well, I hope you watched the video. Were you able to detect the changes? The 21 changes? Get out. Did you say yes? No, it's impossible, right? You cannot because your mind is tuned to only pay attention to parts of the scenes, not the entire scenes, right? So if you're not paying attention to something, then you will not recognize that there is any change, correct? So this fact that you did not notice any change in the scene or all of the changes in the scene in the video has to do with the fact that you did not pay attention to it. Remember, your eyes capture information, a lot of information, but you only pay attention to part of it. And that part of information is kept track of from one fixation to another fixation, moving that captured information to your short-term memory, and that's what is remembered. For the rest of the items you did not pay attention to, but your eyes captured anyways, you assume that things are unchanged, they remain the same until you realize that it's not the case, which I hope you realized when you watched the video. So do we keep track of objects from one fixation to another fixation? Yes, but only a part of the captured information. That part that you paid attention to, not everything. Everything else we assume remains same. And the part that you captured is sent to your short-term memory during each fixation, even across saccades. That's why it's called transsaccadic memory. And this memory for the objects you're paying attention to in your short-term memory is stored as object files. To sum up what we have learned in this video, bigger picture, how do we gather visual information? Because this is sensation after all. How do we gather information? During fixation, your eyes captured the information. And only during the initial 50 milliseconds of the 200 millisecond fixation is when your eyes capture information. For the remaining 150 milliseconds, your brain attends to and perceives that word. Then the perceived word is what is sent to your short-term memory at each fixation. And you have memory for these words even after the fixation across saccades. That's called transsaccadic memory. And we store this transsaccadic memory as object files. Well, that brings us to the end of detailed information about sensation. It also lays foundation to perception. In the next video, which is the last video for this particular unit, we'll talk about perception. Remember, perception is interpreting what is captured. If you look at it, you're capturing information during a fixation and you're only capturing during first 50 milliseconds. What you're doing with this captured information for the remaining 150 milliseconds is perception. And we'll talk about this perception. So perception happens at each word in the context of reading. I'll see you in the next video. Thank you very much. I hope you're enjoying these videos. Stay tuned and have fun learning.